And what we're talking about are these typing judgments. This is part 3 of the course. Part 1 was syntax. What is stuff? Part 2 was how do we get a value for our stuff? Part 3 is this stuff, what types does it have? What's the sort of stuff? Can we say something about the nature of the stuff? Not its value, but its nature. Is it a function? Is it a number, etc.? And the advantage is we can trap errors without having to run the programs. So we invented a new judgment form. A new judgment form. And it looks like this. So you have a context, and there's this symbol, proves. I guess it could be entails. Oops. Entails. And then a term, and then this is has type, and then whatever the type is. So it's a whole new judgment form. One of the nice things about this course, and I guess I have to thank Connor for this, is that he's presented this nice uniform way. Everything is about syntax and judgments. It's very rigorous, it's very precise, and when you get the hang of it, that's really advantageous because you know exactly what's going on. I can imagine this course being taught by other people with vaguenesses here and vaguenesses there, and that can be confusing. Anyway, so what are these contexts? Well, it's another grammar. A context is either empty, or it's a context you've already built, and then a comma with a variable, colon, and then a type. And if you remember, the types were either natural numbers, or they were a type, arrow, another type. I should say that, of course, in more advanced programming languages, you get more and more types, and actually, the department here is one of the world's best departments for producing new type systems. So that's one of the things we actually specialize in, so it's lovely to talk about it. That's one of the things we do research in. Okay, so we said what a context is, we said what the judgments are, the forms of the judgments, and now, not surprisingly, all we need to do is go through and write typing judgments for all the forms of syntax, just like we had evaluation rules for lambdas and additions and variables and applications and numbers. We're going to do the same for these typing judgments. And so we got as far as this one. We said, where should we start? And you all looked so keen and so eager that I thought I'd let you do it. And we were doing, how can we work out the typing judgment for a plus? So a plus looks like this, and we want to know, when can we say, in what context? Got it there. In a context, gamma, when does this context entail that this term has this type? And I guess going back to this thing about contexts and environments and memories, this is another form of memory. It's just the variables are now being given, not values, not other memories and other values, but they're just being given types. So we're always saying, if the free variables have this stuff, your overall term has that stuff. Okay. And the only other thing that's on this slide was just to remember that this has type. This is pure syntax. You know, there's no sets of the kind of mathematical world that people use to model stuff. This is just language. I've told you what the types are, and this means has type. So that's what we're talking about here. That's not quite the same thing as belonging to a set, but in many ways it's very similar. And we'll talk about that later. But anyway, so we're doing this one. So in order to find when does t plus s, when is that a natural number? We know it's not a function type, so there's no rule for a function type for t plus s. When is it a natural number in this context? We started doing it, and we got to the stage, well, t better be have type nat. Now, who's it going to ask next? Where do we get to? Stick your hand up. You can you remember? I'll have to choose something at random. Silence. Okay, I'll choose something at random. No volunteers to start? Volunteering is always good because then you're in control of your own destiny. No, all my entreaties to step forward, all falling on stony ground. No one wants to step out confidently, be bloody, no, not bloody, that's Macbeth. Be bold and resolute. Absolutely no one. All right, right from the far back. Yeah? You with me? Good? Okay. So we're trying to prove this, and certainly we've got the idea we should check that t is a natural number, but what else do I need to write?
S colon.
Yeah, that's fine. Don't need to do too much. Okay, so certainly we should check that s is a natural number. So I heard s colon. So we're going to check that s is type natural numbers. So that's a good part of doing that. Your turn next. Want to fill in a bit more?
Well, the rest of S.
Pardon?
The rest of S. So S has to be a natural number.
Okay, so it has to have type nat, not type n. That's good. Now we're not quite done. If you think we're done, you've forgotten that our judgment forms are context, entails, term, has type, a particular type. And that's what we've got at the bottom, but these two aren't in that form yet. So there's bits missing. So I need to put them in here. So that's the hint. Okay, next. What should I, so this is not complete. What should I write here? Okay, well, we've got the type, we've got the colon, we've got the term. Yeah, okay, very good. See, it's not so difficult. I think learning, my experience after teaching for decades, is that often, it's like just getting started. Is it really this? Is it really that? Once you get started, it's not so hard. So that's why I'm trying to get everyone started. So yes, you just have to follow the grammar of the judgment form. This tells you exactly what it should look like. And now tells you, I need a context. Someone has to write a context here. And by the way, there's only one possible context you can write. There's only one thing on the board that makes sense. So, what is it? The gamma, yes. So gamma is this context. That's a capital gamma. I apologize. I'm not quite sure why. Why is all of mathematics written in Greek? Because they did it first, I guess. Anyway, so yes, you get a free class in the Greek language at the same time as this. Okay, so in order to check that in the context gamma, remember this context is telling you the types of the free variables. So if when the free variables of t and s are given types in gamma, to show that t plus s is type natural numbers, you need to show that in this context, t is type nat. Very good. Your turn next. What about this? We've not quite finished this. Yeah, entails. Okay, and your turn. Yeah, fantastic. So I didn't need to do anything at all. You all worked out your own inference rule for yourself. And I guess this is a bit like the last part of the hand-in that you're doing at the minute. This is the creative part. Once you get given this rule, everything is formulaic. You follow the rule. But now we're being creative. We're actually generating the rule. And it's just straightforward. When can this have type n? Well, t better have type n, s better have type n, but I need to use the correct judgment form, so I need these parts here. Okay, very good. That's one rule. Okay, so there are 5 bits of syntax in the lambda calculus: pluses, numbers, variables, application, and abstraction. So we're just going to go through the rest of them. So, what should we do next? Should we do numbers? So, when will a number have a certain type? Now, again, numbers can't be functions. They're not functions. Guess what? They're numbers. So there's only a rule for saying when n is a number. And the judgment form will have to have a context. Now, it so happens that n doesn't contain any free variables, but it might be part of a bigger expression which does it have free variables. So you might want this gamma there anyway. So when can gamma show that a number is actually a natural number? Your turn next. What should we write above the line? What do we need to do to check that this number here has type nat? Yeah, so we're trying to check that n has type nat. Under what circumstances does it have type nat, do you think? If I said 5, is that a natural number? Do we need to check anything about 5? But do you think is 5 a natural number? Yes. Do you need to check anything? No. What about 7? Do you need to check anything about 7? Alright, so in general, do you need to check anything? So here, n is a natural number. All numbers have type nat. Nothing to check. There's no subterms, there's no variables. It's just given for you. So there are no premises. So this is like when we had, when you try to evaluate 3, the answer is just 3. You don't need to do any more work. So it's like a base case. So that's fine. That's a rule for natural numbers. Under no assumptions at all, any number has type nat in any context. Okay, what else do we have? Plus variables. Let's do variables. Okay. Now variables. So we're going to try and give this variable a type. And variables, they could stand for natural numbers, but they can also stand for functions. So in fact, this could be any type. Actually, what letter are we using for variables? Let me check. Type sigmas and taus, okay. So, this is saying, when does this variable have type sigma, and sigma could be nat, but it could be nat arrow nat, or it could be nat arrow nat, it could be any type at all. Right, what do you think we should do? Yeah, you need to check it, indeed. But where are you going to check? You can't ask me, because I don't know. Well, we're going to find out when X has type sigma. Right, so when does X have type sigma? The only thing you can check, I'll give you a clue, it's something to do with this memory. Remember, the memories, or the environments, that's what tells you information about variables. Whenever you want information about a variable, you look in the memory. The memory stores information about the variables. So we should look inside the memory gamma. So, what did I write down? I wrote down. Oh, wrong place. Oh dear. So remember this context. This context is built of all sorts of things that look like this. Variable has a certain type. And if the variable has a type in the context, then that variable has that type. That's like saying, I want to find the value of x in a context. Well, if in the context x has the value 5, then x has the value 5 as my evaluation. Okay, these are very simple rules. And again, you don't need to, there's no smaller parts that you can check. So, right, that leaves us only 2 to do. So the first one is abstraction, and the second one is application. So let's do application. So I want to ask, when does f applied to s have type tau? What do you reckon? Can you? These last 2 ones, of course, are the most sophisticated, because it's always application, always abstraction that are most sophisticated.
Do you have to check for f?
Mm-hmm.
To check what type it is?
Yeah. So in all these things, when you've got a big term that's got components, of course, you have to check the components. To evaluate a big term, you need to evaluate the components. Similarly here, if I'm going to figure out the type of f applied to s, I should figure out the type of f, and I should figure out the type of s. So, well, I won't do this. Right, so that's good. So we can write something down already. What should we write down? Okay, very good. I want to check the type of f, so I better write down f. Your turn next. I want to check the type of f. So I've got my judgment form, which looks like things like this. Context, entails, some term, and I've got my term, colon, a type. So what should I do with f? How can I... Yeah, I need to check the type. F could be a complicated thing. It's not necessarily a variable. It could be a... But I need to check its type. So what should I write here? Here. Remember the judgment form. You have to give me a context. You have to give me a term style. You have to, entails. You have to give me a term, you have to give me a colon, and you have to give me a type. That's what this says. To check the type of something, you must give me a context, you must give me the symbol, you must give me a term, you must give me a colon, you must give me a type. You can choose from those. 5 options. You can't choose the term because you already got F. Yeah? So certainly, let's have that. Your turn. 3 more options. Yeah. Entails. Okay. So there's 3 gone, 2 left. Your turn. What context should we use? Yeah. Okay. Right. Let's pause there for a minute. Actually, well, maybe. Now there'll be some. So far this has been quite trivial. F, colon. But there'll be some work to be done here. Your turn next. What do you think?
T.
Well, if F applied to, so remember, this is a function that takes some input and returns some output. And S is the input. And the result of F, the output type, will be tau. But F itself doesn't have type tau. Sorry, that's more Greek, tau. You can call it T if you like. But then don't use T for a term. But anyway, so F can't have type tau. F must have different type. F must be a function type. It takes input and returns output. So I'm going to write the function type there. And then we're going to have to say, put the input type here and the output type here. And we're also going to have to work on S. Okay, so it's good to try, but as I said, this was the most imaginative part. Go to next.
So we're looking to the memory, see the type?
No, because actually F is a big term. Only variables do you look into memories. And we've done the rule for variables. Now, F might contain variables, so later on, when you build this tree up, you'll go into the memory. Could have been right. I mean, I know F looks like a variable, it actually stands for a big term. Any other ideas? Okay. Well, how about working out the type of S? What should we do to work out the type of S? Remember, you've got to use a judgment form. So, you can give me either a context, or a turnstile, or a term, or a colon, or a type. And we're trying to work out the type of S. So you've got 5 options. Which of those do you want to do? Do you want to give me the colon? Or do you want to give me the turnstile? Okay, yes, well that's part of the judgment form, so we can... I think when you're doing stuff and it's new, always good to write down the stuff you know. You may not know the whole answer, and you try to wait till you know the whole answer to write the answer down, you'll get stuck, because you don't know the whole answer. So if you start writing down the things you know, you reduce the amount of work you have to do. And you know, if we're going to work out the type of S, we have to write colon. So you may as well put that down. Your turn next.
Well, we obviously have to check the type of S
Yes.
in this case.
Okay. So what should I write down? Either the context, the turnstile, the term, or the type.
So we would write down the term before the colon.
Okay, and what's the term that we're checking?
S.
S. So I should write down S. So I'm going to check the type of S. Very good. Might sound painful, but that's only because you're doing it for the first time. Your turn. I promise you, after 20 years, I can do it in my sleep.
Would you then put the turnstile?
Yeah, exactly. I've told you. Got to write a turnstile. So no thinking required. You can always write that down. Okay. Your turn next. You can either give me the type for S, or you can give me the context.
Context?
Yeah. And what's the context?
I don't know.
Okay, well, the context will tell you the variables for S. Okay, and there's only one context available to you. Have a guess. That's a type, that's a colon, that's a term, that's a term, that's a entail symbol, that's a context, that's a context, that's an entail symbol, that's a term, that's a colon, that's an arrow. There's only one context that you can use.
Is it that? Like, I don't know what to call it. The,
Capital Gamma.
yeah.
I could try and use English letters if you want. Okay. Yeah, there's only one context. Gamma was giving you the 3 variables for F and S, so it'll certainly give you the three variables for S. So that's mostly done. Now we just got to work out the types. So we've got, the clue is this overall thing must have type tau. So we better use tau somewhere. So here's a question. Whose turn is it? It's your turn next. So that means this function f takes an input and returns an output. S is the type of the input, and tau is the overall result. So where should tau sit here? Here, here, or here? What do you think?
At the far end.
Here?
Yeah.
It's not that, because this is the type of S, okay? Whereas this thing here has type the same thing as the output of F. S is the input of F. So I'll get that to that later. But this is the type of this, tau, is the type of the output of F. F says, give me something, which S has the type of, and I will return something of type tau. So, well, we know, yeah, that's what we're trying to do. So we know that F, it takes an input and returns something of output. So these types we have to fill in, and one of them is going to be tau. Have a guess. Hmm?
I'm not sure.
All right, okay, it's tau. So, this says that F, we have to check F is a function which returns a tau. And that means if we give it an input, guess what? We'll return a tau. Okay, what about the input type of F?
I'm not so sure.
Yeah. Well, that's not surprising. So this rule doesn't say, we haven't got enough information to say anything concretely about the type of the input of F. We know it's the same as the type of S, but that's all. So in fact, it could be something else. So it could be some signal. So this says, if F has type, a function which takes something of type sigma as input, it'll return something of type tau as output. So that means when we give it some input, we get the output. But now we can say what the type of S must be. Yes. So F is saying, I'm expecting something of type sigma. I'm expecting something of type sigma as input. There's my input. Oh, it better have type sigma. Finally, we want to work out when the lambda abstraction has a certain type. And now, I know this lambda abstraction, it can't be a natural number. Lambda abstractions are never natural numbers, they're function types. So therefore, the only thing I can show is it has some type, a function type. So when does this thing have this function type? I.e., when is this expecting something of type sigma as input, and it'll produce something of type tau as output? Okay, again, this is quite, requires quite imaginative thinking. I'll try and help you. Maybe you don't need my help, of course. Yeah, very good. So, as always, if you want to know what the type and the value of a big thing is, you have to look at the smaller things. So we're going to find out what the type of lambda x arrow t is, we better find out what the type of t is. So that's what we're going to do work on. And remember, context judgments are 5 things: a context, entail symbol, a term, a colon, and a type. And we've got the term. So there's 4 more things to put up here. Your turn next.
I don't know what's going on.
You don't know what's going on. Okay. Have you been following some, or do you need to start at the beginning?
Nah. I'm having lots of trouble following it in general. My brain's kind of zoned out.
Okay. Shall I skip you, or shall I try and help?
Probably best.
Okay. All right. That's what? Your turn. Colon. Yes. There were 5 things in a context judgment. One of them has to be a colon. So let's put the stuff down that we know. 3 things left. It's like a clock ticking down, isn't it?
Entails.
Entails, yeah? So, always put the easy bits down. So we're trying to find out the type of t. We're going to say, in some context, we can show, or it entails, that T has a certain type. Right. Where now? Your turn.
And the capital gamma before two.
Okay, that sounds good. Right. That sounds good. That's it? You look. Okay, let's have a look. What type, so T is going to produce the output, isn't it? T could be like, X plus S, it takes X as input, it does all sorts of things, then produces an output. So what type better the output of T be? Do you think it should be sigma or tau or something else? Remember, this is a function that takes something of sigma as input and returns something of tau as output. Tau, yes. I'm not sure if that was how much certainty there was there, but yes. So, if this function is going to take something of type sigma as input and return something of type tau as output, then T better be returning that thing, something of type tau as output. Okay? So, we've got 5 things down on the page, so it could be that we're done. And this is the right form for a rule, but actually it's not quite right. And the reason it's not quite right is, remember, this gamma should be telling me the value, the type, of all the free variables in my term. But T has an extra free variable, the X. And gamma isn't telling you what the type of X is. So we actually have to change this context to put in the type of X. So the first thing is, what should the type of X be? Remember, X is the input to this function. So what do you think the type of X should be?
I'm not sure.
Okay, well, there's only one thing on the page, it's sigma, because remember, this is a function that takes something of type sigma as input. That's what this type says. And the thing it takes as input is X. So X better have type sigma. Okay, so we know X should have type sigma, but we've got to put it in the context. So how do we write that? Yes, we certainly want to write X. Good. Again, I can show you the, see, it's all written out for you. Context look like this. So if you want to extend a context, which is what we're doing, we've got to write the previous context, and we've done that. Sorry, you can't tell me gamma for the previous context, we've done that. Then we need a comma, which we haven't done. Then we need a variable, and that's the bit you've just done. And then we need a colon, which we haven't done. And then we need a type, which we haven't done. So far we've got 1, 2, 3 things left to do. Okay, so here we are. 3 things missing. Which of them do you want to do? Yes. So in this new context, we're saying X is going to have type. What type shall we give it? No, don't say it. You'll take away his fun and his chance to learn. And he'll be bereft and scarred for life.
Sigma.
Sigma. So we're going to say sigma. And the last thing.
The turnstile for the X.
No, because this is a context we're building, not a typing judgment.
All right. Okay.
Remember, this is a typing judgment, so this is a context. It's a good guess, but it's not quite. Get in?
Me.
No, no, no. Unless you're sitting next to. I guess you can't see behind you.
I don't know.
Don't know. Okay. Well, let's have a look. This is a context. Agreed? Is this a context? Well, it is a context.
No, you don't have a comma.
Thanks. But again, if you do, I mean, I go through this process, and it might be slow. And if you know the answer, I'm really grateful to you. But if you give the answer, then I can't help people who might want a little bit more help. So please don't shout out the answers. It will take longer, but I think over my experience, I prefer to try and help everyone. So that's why I do it this way. Anyway, there you go. So there's 4 rules. There we go. So, those are the rules for typing derivations in the simply typed lambda calculus. It's quite small. It's new to you. It's written out very formally in context and judgments, so it takes a while getting used to it. But actually there's not many of them. And I went through it slowly because I hope you've got a handle on the intuition behind it. If you don't understand the intuition, all the symbols, I mean, sometimes I think it can make you feel dyslexic, you know, the symbols start swimming around. But if you understand the intuition behind it, it should be straightforward. To work out the type of T plus S, you have to work out the type of T, the type of S, check they're all natural numbers, and use the right context. So the rest of this lecture, we'll just do a few examples. So I will try and leave this here. I need more space. Ah! I've got a board. No, I haven't got a pen. Right. We'll have to do it in this space here. Right. So there's the term. I haven't got enough space. I need new paper. So I want to work out what the type of lambda x arrow x plus 2 is. Okay? Now, I know that there are no free variables, so I've left the context empty. I know there should be a function type, because lambda is a function, so I'll write the arrow in. I don't really know what sort of function type it is, so I'm going to have to do some work to get these. It's just going to be like building these natural deduction trees you've done before, except the rules are slightly different, the rules we've just got. So, where should we start? So, we've got some, right. So the rule for addition is not on this page, but I'll remind you of it. So these are our rules, and this is the problem we've got to do. So, now where do we get to? You want to have a crack, because you were robbed of the chance to do it previously.
Well, we need to find type of x.
Okay, almost, but not yet. This is a lambda term. So we don't use the rule for variables. We have to use the rule for lambda terms. Later on, of course, we will do. You're jumping ahead because you're pretty smart. I can see you're keen and eager to get on with it. But just to be very slow, this is a lambda abstraction, so we have to use this rule. So your turn next. How do I use this rule? What should I write above here?
Not sure.
Okay, well, so if you look at this rule, can you see down here?
Yeah.
Yeah. So it says there's, we can have a look. What's in this example, the gamma is empty. We've got the term t is x plus 2. And we don't quite know what sigma and 2 is. So we know that t is x plus 2, and we know that gamma is empty. So we can start filling the top line. So what's gamma?
Is nothing.
Nothing. All right. So we've got nothing. So that's where we start. But then we have a comma, which I won't write because it's a bit silly. So the next thing is the variable. So your turn. What variable should I use? In my example, x. Yes, it's still x. It hasn't changed. Okay, so I should write x. Okay. Oh, so sorry, I took colon off you. Right. So I wrote x, and then I should have said what comes next, and you should have said colon. But unfortunately, I wrote colon. I was too quick myself. So the next comes the type of x, sigma, which is this. In our example, that's here. So we don't know what it is yet, so we can't do that. So we'll just carry on. So I'll just leave a blank there, we'll come back to it. So what shall I write next?
Tail symbol.
Yeah. So we're going to have to find, in this context where x has some type, we're going to show, or entails, now we're going to have to write our terms. So what's t? What should I write? Your turn?
The symbol.
I've got this one already. So now I'm writing the term.
Brackets, x plus 2.
Yes. So I'm going to have to show x plus 2. That's the term. What should I write next? Colon. Yeah, getting quicker. Right, and now the type tau, but again, I don't know what that is yet, so I'll wait a bit until I find out. So now we've got a plus formula. So I need this rule. This is the rule for doing plus formulas. I've got a plus formula. Okay, did you? Your turn. So,
Draw a line.
yeah, draw a line. I'm going to use another rule. So, I'm building up my tree. Your turn.
Got kind of type of X.
Yes, so that's right. So the first thing I have to do is find the type of t, which is x. So I'm going to have to find the type of x. What else should I write? Colon. Very good. Your turn. So here's the rule. So t was x, and I wrote colon. What do I write next?
The natural.
Yeah, because if I'm using the addition rule, I can only add up natural numbers. So I'm starting to work out the types of things. X will have to be a natural number. Your turn?
Do you want the turnstile?
Yeah. Because this has to be a context judgment. And now the question is, so I'm doing this part, I've got my t, which is x, I've got my n, I've got my colon, I've got my turnstile. What context should I use? No, I shouldn't ask Ben. He's not paying attention. Your turn.
Is there no context?
Let's have a look. Oh, there is a context. So it started off with no context, but actually now we're doing this typing judgment, and there is a context, because we need to know what x is. So, what
So
should I
the
write?
context is X.
Yes. So the context should be x. Right. Right. And now we can start filling things in, I guess. We're going to soon figure out what the type of x has to be in the context. Your turn? What do you want it? So, how can I show, if I want to show x is type n, so where's the rule for variables? There it is. What type had x better have? N. You sound nervous, but yeah. So, I can complete this part by saying if x is type n in the context, then I can show entails x is type n. Wow, I know it's stunningly surprising, but at least it's rigorously precise. And now that I put n here, I can write n here. Okay. And I'm just slowly doing this detective process of finding out stuff. Right, so I'm trying to work out this rule, and I've got the type of x, and I've completed that judgment. So now I should go on and think about the typing for 2, because I'm back to using this rule for plus. Your turn? Yes? I think it's it here.
Would you have the just the two that's like
Yeah, exactly. So, we know what the type of 2 is. Obviously, it's a natural number, but we're just using these rules and getting practice. So to show that a plus thing has a type, we first of all have to work out the type of the first part, which we have, and then we have to work out the type of the second part. So that's 2. So let's work out the type of 2. So I'll write 2 down.
Will we have the colon?
Yeah, it's a typing judgment, so it has to have a colon. Yeah, and if you look at the typing rule for natural numbers, the only type natural numbers have are n, so that's fine. I need to put a context in, so I'll do that. So the context has to be this, so I'll put the turnstile in, I'll put the x is type n. So even though 2 doesn't use the fact that x is a natural number, it's got to be there to be a proper typing derivation. Okay, so your turn. Sorry, did I ask you already? You did it? Yeah, so it's you. Yes? So we've got this, what goes here?
Natural number.
Yes. Because the rule for addition say that in the conclusion, you always get a natural number. So if x is a natural number, x plus 2 is a natural number. And that's what we proved using formal derivation. So now we're going back to this rule. So we originally tried to do this. The context was empty. There's our turnstile. There's lambda x. This was our t. And then it has some function type. And in order to do this, we're looking for a judgment where we have a context which is empty. Then we have x gets given a variable, then x gets given a type, then t gets given another type. So sigma is a type of x. So what goes there? Oh, all the way back to the beginning. Go to. Yeah. So sigma, the input to the function type is just the type of the variable. And the type of the variable is n. Sorry, you said sigma. I said yes. Right. In general, yes. But in this specific example, what goes here is the type of x. And we worked out the type of x had to be n. Okay? Go to the next. So in this example, what goes here? What goes here is tau, which is the type of t. And the t is x plus 2. So what's tau? What goes here?
N.
N. It's just the type of x plus 2. There you go. There's one typing derivation. Okay, so there's one example. Let's do another example. Let's give you an example for homework, I should say. So, okay, so that's for homework. I want you to show that in the empty context, we can show, it entails, that this big term has type nut. That means it's a well-typed term. That means, you know, we've got none of these additions of functions to numbers, errors. Okay? So that's homework for free. And can I ask one of you to remind me to tell you the answer at the beginning of the next lecture, I guess. Thanks a lot.